In this video, I will demonstrate how to perform a multivariate analysis of variance, also known as a MANOVA. This technique is an extension of analysis of variance, and we use it when we have more than one dependent or outcome variable. Now, these dependent variables typically are assumed to be related in some way, or there should be at least some conceptual reason for considering them together or measuring them together. So MANOVA compares the groups and tells you whether the mean differences between the groups on the combination of the dependent variables is likely to have occurred by chance, or is it due to the effect of the treatment or the group designation. So in order to do this, MANOVA creates a new summary or aggregate dependent variable, which is basically a linear combination of each of the individual dependent variables. So it then performs an analysis of variance using this new combined or aggregate dependent variable. And so then MANOVA will be able to tell you if there's a significant difference between your groups on this composite dependent variable. And then if there is, you can then look at whether or not the treatment has an effect on the individual dependent variables one at a time. So some people might say, well, why not just do a series of ANOVAs separately for each outcome or dependent variable? And many researchers will do that. Unfortunately, by doing a whole series of analyses on the same grouping of data, you run that risk of an inflated type 1 error. And this is similar to what we run into with doing several t-tests as opposed to doing one-way ANOVAs. So the more analysis you do, the more likely you are to find a significant result, even if in reality there's no difference between your groups. So we could have a greater type or inflation of type 1 error. So the advantage then of using MANOVA is that it controls or adjusts for this increased risk of a type 1 error. But the cost of that is it's a much more complex set of procedures, and it has several assumptions, additional assumptions that need to be met. Now, if you decide, well, MANOVA sounds too complicated for me, I don't really want to do that, I'd rather do a series of individual ANOVAs, you can still do that, but what we'll need to do is, in order to reduce the risk of a type 1 error, you'll need to set a more stringent alpha value. And one of the ways to do that is to perform the Bonferroni Adjustment, which is where we take our normal alpha level, which you're going to test the hypothesis at, in this case maybe 0.05, and then divide it by the number of tests that you intend to perform. So if you have 3 dependent variables, you would divide 0.05 by 3, which works out to be 0.017 after we round up. And then we would use this new value as your cutoff in order to make your hypothesis decision. So differences between your groups would need a probability value or a p-value of less than 0.017 before you could consider them statistically significant. So MANOVA can be used in a one-way situation, which is what we're going to do in our example here. You can do factorial or two-way, as well as higher order factorial designs like MANOVA or MANCOVA or factorial MANCOVA. So in the example that we're going to do here today, we're going to have one independent variable with 3 levels, and we're going to have 2 outcome variables or 2 dependent variables. So we consider this to be a one-way MANOVA with 2 outcomes. And so what we're going to do in this example is we're going to compare the effect of 3 different types of surgical techniques on shoulder injuries. So patients would be randomly assigned to one of 3 surgical techniques in order to repair a shoulder injury. And the 2 outcomes that we're going to measure are recovery time, which is the number of weeks it would take them to return to being able to perform a list of kind of everyday functional activities. So however many weeks it takes them to be able to do that list of activities without pain, we're calling recovery time. And then we're also using what's known as a global rate of change, or GROC scale. And this is a subjective measurement that patients will give us to tell us how much improvement they may have received after the intervention, in this case the surgery. So this GROC scale ranges from -7 to +7. And so a +7 score would mean they had very significant improvement in their condition. A -7 score would indicate that they had very significant worsening of their condition. A score of 0 would mean there's really no change. They're no better off and they're no worse off. So those are our two outcomes. We're going to measure what effect the technique has on recovery time. Presumably certain techniques will have a faster recovery time than others. And then we're also measuring this global rate of change. Presumably certain techniques will have a greater level of improvement versus worsening. And so we're going to compare those two things. And so we have one, in this case, categorical independent variable with 3 levels. We have 3 different surgical techniques. We have 2 in this case, or we could have more continuous or quantitative outcome variables that we are going to presume are somewhat related to one another. So it's by intuition we would assume that recovery time and improvement or lack of improvement will be related to one another, and we're going to test that. So we've got several assumptions that we need to test with MANOVA, and some of these are going to sound familiar from doing ANOVAs, but there are some new additional assumptions that we need to look at as well. One of the assumptions, the first assumption is sample size, and I'll talk about these in a little more detail as we go through our example. But we have sample size. We need to test the normality of the outcome variables. We also need to make sure we don't have any outliers present. We need to make sure our variables are linearly related. We also need to make sure there is not any multicollinearity. And I'll explain that in a little bit. And we also need to make sure we have homogeneity of variance as well as homogeneity of covariance. Okay, so let's look at the assumptions first. Sample size is the first one. And here we typically use a rule of thumb if we need to have more cases in each group or more subjects in each group than we have dependent variables. So ideally we'll have many more than this, but this is kind of the absolute minimum. So having a larger sample can help us kind of get away with violations of some of the other assumptions like normality or some of the other things we can look at. So the minimum required number of cases in each group in this example would be 2 because we have 2 dependent or outcome variables. Now we have a total of 6 groups. We have 3 levels of our independent variable. Surgery technique number 1, 2, and 3, and then we have 2 dependent variables. So we have a total of 6 groups here. So the number of cases that we're going to see in each group is going to be provided as part of the MANOVA output, and then we'll be able to examine whether or not we've met that assumption. Now the next is normality. And so even though the significance tests of MANOVA are based on the multivariate normal distribution, so in practice it's pretty robust and it's able to deal with modest violations of normality, except where the violations might be due to outliers. So when we have a sample size of at least 20 in each group, we kind of assume that's going to be robust enough that we can overcome any differences or any limitations in normality. So we still need to check univariate normality of each outcome, which we do through the explore function and looking at the skewness score. And then we're also going to check multivariate normality, and I'll show you how to do that a little bit later. And so these procedures will also help us determine if we have any outliers. And we can use the outlier labeling technique, as I discussed in one of the other videos, to help us identify if we have any potential outliers. Now, talking more about outliers, MANOVA is very sensitive to outliers. So if we've got data points or scores that are much different than the rest of the scores, so we need to check for univariate outliers, again using the outlier labeling technique for each of our dependent variables separately, and then we also are going to look for multivariate outliers. So multivariate outliers are participants with a kind of a strange, unusual combination of scores on the various dependent variables. So in other words, they might have a very high score on one variable but a very low score on another variable. So again, we're going to check for univariate outliers by using the explore function and then using the outlier labeling technique. Now, in order to check for multivariate outliers, I'm going to kind of walk you through the procedure to do that. So to test for multivariate normality or outliers, we're going to use something called the Mahalanobis distance and SPSS is going to help us calculate that, and we're going to be using a regression function to do that. So this Mahalanobis distance is the distance of a particular case or score from the center or the centroid of the remaining cases, where the centroid is basically the point created by all the means of all the variables. So it's kind of the center score of all created by all the scores. So this analysis will help us pick up on any cases that have a strange pattern of scores across all or across both of the dependent variables. So what's going to happen is this procedure will create a new variable in our data file, and it's going to be labeled MAH_1, and you'll see that when we run the analysis. So each person or subject receives a value on this variable that indicates the level or the degree to which their pattern of scores differ from the remainder of the sample. So to decide whether a case is an outlier, we need to compare this distance value against a critical value. And so we use a chi-square critical value table to do that. And what I'll do is in the description of this video, I'll post the table that you can use as a reference to help determine if you've got distances that are outside of the acceptable level. So if an individual's MAH_1 score exceeds this critical value, it's considered an outlier. And so MANOVA can tolerate a few outliers, a handful of outliers, particularly if their scores are not too extreme or not too far away from this critical value, and if we have a reasonable size data file, in other words, a reasonable sample size. So if we've got close to 20 subjects in each cell, and we've got a few outliers, we're probably going to need to delete those. But if we've got 50 or 75 or 100 subjects per cell, we can easily tolerate a handful of outliers. So if we have too many outliers or very extreme scores, in other words, a Mahalanobis score that is quite a bit above the critical value, we're probably going to need to consider deleting those cases or maybe transforming the variables that are involved. So let's go ahead and let me show you how to run this procedure to test for multivariate normality. So the first thing we want to do is go to the Analyze menu. We want to select Regression and then Linear. So we want to enter the variables, or first entering the variable identifies each one of our cases, which in this case is surgical technique. That's our categorical or independent variable, and we put that in the dependent box, which seems counterintuitive, but that's how we run this analysis. And then in the independence box, we put our outcome variables, in this case weeks until return to normal, and then that global rating of change score. Then we click on the Save button, and then we want to make sure we've checked under the distances box, we check that Mahalanobis distance option. And so you can see I've checked that. Okay, once we've done that, we click on the OK button, or click on the Continue button, excuse me, and then we click on OK. Now, if we go back to our data file, you'll see that we have created this new variable, MAH_1. Okay, so that's the variable that we're going to use to help us determine if we have any outliers. Now, if we go back to our output file, okay, the box that we are interested in, or the table we're interested in, is the very last one. It's labeled Residual Statistics. And what we want to look for is the maximum value listed under the Mahalanobis distance row. So here we see here the Mahalanobis distance, and our maximum score is 11.218. Now we're going to take note of that value. In this case it's 11.2, which doesn't seem like a very high value. So we're going to compare this number to the critical value I mentioned earlier. And so this critical value is again determined by using a chi-square table with the number of outcome or dependent variables we have serving as our degrees of freedom value. And then the alpha value or p-value we'll use to determine our critical value is 0.001. So again, I'll put a table in the descriptor for this video, description section of this video, and you'll be able to see this table. and I'll include for studies up to 10 outcomes, 10 dependent variables. So in this case, we have 2 dependent variables. So our critical value for determining if we have an outlier is going to be 13.82. Okay. So if we compare that to our max score of 11.218, we can see our max score does not exceed that critical value of 13.82. So that means we do not have any multivariate outliers. If this max score did exceed that 13.82, then that would indicate we do have outliers. And so if we wanted to define those outliers and take a look at what their scores really are relative to, and how many there are relative to this critical value, we would have to sort the cases. So let me show you how to do that just for demonstration purposes. So in our example, we did not exceed the critical value. So we would determine that we met the assumption of no multivariate outliers. But if this value did exceed the critical value, we need to find those values and how many there are. So we go back to our data file, and we can see here we've got our value. So what we want to do is sort this variable by the value. Okay, so we're going to go to data and then sort cases, and what it'll do is it'll rearrange the data so we have the highest MAH1 scores at the top, and we can see what those scores are and how many there are. And so we move our new variable that we created, this Mahalanobis distance, and move that into sort by. We want to choose sort order of descending, so I'll list the highest scores first. So again, we go back to our data file now, and we can see we've got our highest scores listed at the top and then descending to the lower scores. So here's where we'd be able to examine what those actual Mahalanobis distance scores are. So we'd be able to identify, number one, how large that score is relative to the critical value, and then how many subjects might have scores that exceed that critical value. So again, in this example, we don't have any, but this is where we'd be able to see this. So for example, if one of the subjects had a Mahalanobis distance score that was maybe 1 or 2 times larger than our critical value, then that would be a large difference. And I probably want to figure out how I can either transform the variable or maybe delete that individual. If I maybe only had 1 or 2 individuals that exceeded that critical value, I'd probably leave them. If I had more than about 2% of my total subjects exceeding that critical value, then I would probably have to consider removing those subjects or transforming the variable. So that's how I would deal with determining if I had these multivariate outliers. But again, in this case, we don't have any, so we've met that assumption. Okay, the next assumption we have to examine is the assumption of linearity. And so this refers to the presence of a straight line or linear relationship between each pair, in this case only one pair, of dependent or outcome variables. So if we had more than 2 outcome variables, we'd have multiple pairs of variables that we'd have to determine if they're linearly related. So we can assess this in a number of ways, and probably the most straightforward of this, but somewhat subjective, is to generate a matrix of scatter plots between each pair of variables, again in this case only one pair, and then separate it out by our groups, in this case type of surgery. So how we do this, we go to the graphing function, select legacy dialogues, and then scatter/dot. So we're going to determine a scatter plot here. So we click on the matrix scatter and then click define. And then all of our outcome variables we move into the box labeled matrix variables. So our recovery time in weeks and then our global rating of change go into the matrix variables box. And then in the rows box goes our independent variable, in this case surgical technique. Okay, the next thing we want to do is click on the options button and make sure that we have a list of exclude cases variable by variable. In our example here, we don't have any missing cases, but if you did have missing cases, you would then have them be excluded variable by variable, so that those won't be included in any analysis. All right, then we click on the Continue button, and then we click on OK. And so what we're going to examine down here at the bottom are these scatter plots. And so what we're looking for is to see if there's a general linear relationship here. And so if we were to kind of draw an imaginary line of best fit on each of these, we can see that these generally trend from lower left to upper right. Now some of these look almost more like squares than bubbles that trend. So that's a little questionable that we have a true linear relationship. What we're really looking for are maybe a trend that might have more of a curvilinear relationship. That almost looks like an upside down U, or maybe a right side up U. But in this case, we have a generally linear relationship, but it's a little suspect because we have, especially here, we have kind of a spread of scores. It almost makes this look more like a square than it does like an oblong object. Now this looks a little more linear. It's spread out, but it's a little more linear. This doesn't quite look as linear. So you could argue that we've met the assumption, but we're going to be a little conservative here and say it doesn't look like we've met that assumption. That's okay. We don't need to stop, but we are going to change how we perform, or how at least we assess the outcomes of our actual MANOVA, and I'll talk about that when we get to that point. But this is how we assess linearity of our outcome variables. Now the next assumption we have to determine is looking at multicollinearity. And MANOVA works best when the dependent variables are moderately correlated. We don't want them to have weak or low correlations. We don't want them to be too highly correlated. So for example, if we have low correlations, we should probably consider running separate univariate analysis of variance for each of our outcome variables. If the dependent variables are too highly correlated, this is referred to as multicollinearity. Now, this can occur when one of your variables is a combination of other variables. So, for example, the total scores of a measurement scale that is made up of certain subscales that are also being examined as outcome variables. Also, if we've got two variables that are redundant, in other words, they're measuring pretty much the same construct, we can have this very high multicollinearity. So what we want to do is assess whether or not we have this either too low or too high of a relationship. What we want is kind of that middle range of relationship between these variables. So how we're going to test this is we're going to basically run a bivariate correlation. So we want to go to the Analyze menu, click Correlate, and then Bivariate. And we want to move our two outcome variables into the variables box. So we want to examine the relationship between these two variables. And then we click the OK button. And so what we want to examine here is this R value. So we can see the R value between, this gives us an idea of the strength of the relationship between these two variables. Now R values can range between -1 and +1. So the closer the R value is to 1, the stronger the relationship between these two values, whether it's negative or positive. So what we like to see, what's optimal, is having an R value that ranges somewhere between 0.2 and around 0.8. If it's less than 0.2, these two variables aren't related enough. If it's greater than 0.8 or 0.9, depending on who you read, that's too much of a relationship. So we like the value to be kind of in that middle range of 0.2 to 0.8. So in this case, the R value of our two variables is 0.349, which is in the middle there. Just it's close to the bottom end, but it's in that middle range. So these two variables are related to one another, but not too related. So appears we've met that assumption then of not having multicollinearity, or of not having too little of a relationship, which is we refer to as again multicollinear, or not having enough relationship. So our last assumption we need to determine then is this homogeneity of variance and covariance matrices. So this is generated as part of our actual MANOVA analysis, and the test we use to assess this is known as Box's M test. And so we're going to look at that when we look at our MANOVA output to determine that last assumption. So up to this point, we've met the majority of our assumptions. The only one we're a little skeptical of is that linearity assumption. And so how we examine our MANOVA output will be a little bit different. I'll explain to that when we get to that point. So now our next step is to go ahead and actually perform the MANOVA. And so we're going to, again, perform a one-way MANOVA using surgical technique as our independent variable. And we've got two outcome variables, weeks of recovery time, and then global rating of change. So how we perform the actual MANOVA, we're going to go back to the Analyze menu. We're going to choose General Linear Model, and then we're going to click on the multivariate option. And the reason we're clicking on multivariate is because we have multiple outcome variables. We only have one independent variable, but we have multiple outcome variables. Okay, so the first thing we want to do is move our dependent variables into the dependent variables box. So in this case, that's weeks of recovery time, and then global rating of change. Those go into our dependent variables box. In the fixed factors box goes our independent variable, in this case surgical technique. And then we want to click on the model button. We want to make sure that full factorial is chosen. And we want to make sure that the sum of squares is listed as type 3, and those are the defaults. So those are typically will be in place, but we want to double check that that is the case. All right, then we click on Continue. Then we click on our Options button. And so we want to highlight Surgical Technique and move that over into the right-hand box so we can see the means for each of our groups. And then in the Display box down here, we want to click on Descriptive Statistics. We want to see Effect Size. We want to see Observed Power. And we also want to see Homogeneity Test. And again, that's where we're going to get our boxes test result. All right, then we click on Continue. Now the last button we need to do is address our post hoc tests. Now if we have a significant difference for our aggregate overall variable, we're then going to examine whether or not the individual outcome variables are also showing significance. If they are, then we'll need to do a post hoc on each of those individual outcome variables. So again, we've got 3 levels of our treatment. So let's say, for example, we find significance for our aggregate variable, and then we also find significance for global rating of change. We then are going to want to do a post hoc to see which individual group has significant differences compared to the others on this global rating of change. So we're going to choose post hoc tests. Now, we don't know if we're going to need to use them or not yet, but we're going to go ahead and make that choice now so that we'll have it available to us if we do need it. Okay, so we want to highlight surgical technique, our independent variable, and move it into the right-hand box. And then because we have, it's a one-shot measurement, weeks of recovery and then global rating of change, we don't need to use the Bonferroni post hoc, but we have unequal group sizes, so we want to choose the Chaffee post hoc. If we had equal group sizes, we could choose the Tukey test, but we do not, so we're going to choose the Chaffee test. So we then will click Continue. And then we can click OK. So the first thing we'll see in our output then is going to be our descriptives. So here are the mean scores for each of our groups. So weeks of return to function, here's the mean number of weeks for each group, our 3 techniques. And then global rating of change, again, here's our 3 means of scores. So as we can see here, all 3 groups took roughly the average return to normal was about 14 weeks. And we can see that the average global rating of change for all 3 groups was positive. It's above 0, so they all showed some improvement, but it appears that the standard surgical technique group had a higher or greater improvement. Remember, a score of 0 would mean there's no improvement, negative or positive, or there's no change, negative or positive. So everyone had a positive change. Now, one of the first assumptions we can look at is that sample size assumption that we talked about. In each group, we took the number of independent variable levels that we had, in this case 3, and multiplied it by the number of outcomes we had, in this case 2. So that would give us a situation where we want to have at least 6 subjects in each cell, and we obviously have many more than that, and we also have more than that kind of 20 number that we think of as being another minimum rule of thumb. So we've got way more than that. We've got good sample sizes. As a matter of fact, our first two groups have very large sample sizes, over 250, but our third group still has a decent sample size, close to 100. So we seem to have met that assumption, as well as having adequate sample sizes. Okay, the next thing we want to look at is Box's test to determine if we have met that assumption of homogeneity of variance. And what we do is we look at the SIG value, which is the bottom value in the box, and we want that to exceed 0.001. Okay, if we feel, or if we see that we've exceeded 0.001, then we have not violated that assumption of homogeneity. So in this case, our significance value is 0.961, so that's way above 0.001. So we know that we have equality of variance for the aggregate outcomes. Now we're going to test the equality of variance for the individual dependent variables in a few minutes, but we've met the assumption for Box's test, so that we're in good shape there. Now the next thing we want to do is examine whether or not the independent variable had an effect on the aggregate outcome. So again, we took those two dependent variables and we have kind of an aggregated outcome that we want to see if the treatment had an effect on it. Okay, and so when we look at the multivariate test table, this is what's going to tell us whether or not the treatment had an overall effect on the variables, the outcome variables. So we want to find the part of the table that's labeled surgical technique. And the first two rows you'll see here are labeled Pauli's trace and Wilks lambda. Now we can use either one of those F-scores to determine whether or not we've met the null hypothesis of no effect of our independent variable. Now if we've met all of our assumptions that we've talked about up to this point, we would use the Wilks lambda to make a hypothesis decision. If we have violated an assumption, in this case we talked about we may have violated the linearity assumption, we would then use Pauli's trace. So for example, if we violated normality, if we violated the linearity, if we violated Box's test, if we violated any of those assumptions, we'd want to use Pauli's trace to make our initial, what we call our omnibus F test, to determine if the aggregate outcome variable has been affected by the treatment. So in this case, because we were concerned about that linearity assumption, we're going to use Pauli's trace to make that decision. So we follow that over and we look at our F-score. In this case, it's 5.208. And then we find the significance value associated with that. That is less than 0.05. So we can make the assumption, or make the conclusion, excuse me, that the treatment, surgical technique, has an effect on the aggregate of our outcomes. So we've kind of met our first hypothesis decision, or made our first hypothesis decision. We're going to reject the null hypothesis and say that the treatment did have an effect on the aggregate outcome. So we can move on and do more additional analyses. So we can also look at the partial eta squared, which is the effect size. And if we multiply this by 100, that'll give us a percentage. And what this percentage will tell us is what percentage of the variance in the outcome variables is explained by our treatment. So in this case, we've got a fairly small percentage of outcomes or of variance that's explained by our treatment. So only about 1.5% of the variance in our aggregate outcome is explained by our treatment. So that's not a lot of effect. So that's a pretty weak effect size. We can also look at the observed power. We have very adequate power. Again, if we have a 0.80 value or greater, that indicates that we have adequate power and we're likely to see the same result the vast majority of the time. So if we were to do this 100 times, about 97% of the time we would see the same statistical significance. So that's a good thing as well. So now that we've looked at the first null hypothesis and we're able to reject that null and say that the treatment did have an effect on the overall aggregate variables, we can move to the next level. And now we can start to look at the effect of the intervention on the individual outcomes. In other words, weeks of recovery and then global rating of change. So the next thing we can examine then is Levine's test to see if the individual outcomes have equality of variance. And we're going to use, in this case, a significance value of 0.05. And so both of these significance values are greater than 0.05. So we've met the assumption of equality of variance for both of our individual outcomes. So that's also a good news. So we've met that assumption. Now the next thing we want to do, and the next table we can look at, is labeled test of between subjects effects. And this is going to tell us the effect of the treatment on the individual outcomes one at a time. So we're going to look at the effect of surgical technique on weeks of recovery by itself, and then surgical technique, its effect on global rating of change. Now when we do that, we're going to have to adjust our p-value that we're going to test for statistical significance. So we're going to use the Bonferroni correction in this case. So we're going to take our original p-value of 0.05 and divide it by the number of outcomes that we have, in this case 2. So that gives us a new significance level of 0.025 that we're then going to use to test for significance to see if the surgical technique had an effect of our individual outcomes. So what we want to do then is go to the section of this table labeled surgical technique, and you'll see our two outcomes have separate rows. So the first thing we can look at is weeks until return to minimal function. So it's our recovery time. We follow that line over to our p-value of 0.090. Now this is not less than 0.025. So we'd be able to accept the null hypothesis at this point and say that surgical technique did not affect recovery time. If this value is less than 0.025, we'd be able to say it did affect recovery time. There are significant differences somewhere. But at this point, we'd have to accept the null and say that recovery time is not affected by surgical technique at a statistically significant level. So we can accept that null, and we can stop with that particular dependent variable. We don't need to move on and do any additional analysis. Now for global rating of change, the one right below it, we do the same thing. We follow that over to the significance level, and this value is less than 0.025. And so we'd be able to make the conclusion that surgical technique did have a significant effect on global rating of change, and there are significant differences somewhere among our groups. So now we're going to be able to move on to doing post-hocs to figure out which groups are different from each other on global rating of change. So we're able to reject our initial null hypothesis on that aggregate outcome. Then we looked at the individual outcomes, and for recovery time we accepted the null, saying that the treatment had no effect on recovery time. But for global rating of change, we're able to reject the null and say that treatment did have an effect on the rating of change outcome. So now we can move on to do post-hocs for global rating of change to see which techniques were different from each other. So now we want to move down and find the post-hoc results, which are listed here as multiple comparisons. And so again, we're just interested in global rating of change. That's the only outcome that had significance. And so first we're going to compare the standard surgical technique to technique number 1, new technique number 1. And we can see the significance value shows that there is significant differences between these two techniques. Now we look at standard technique compared to new technique number 2, and we can see that there is no significance. This value is greater than that 0.025 value that we're using as our new significance value. So we would say that there is no difference between standard technique and technique number 2. Now we can also look at comparing technique number 1 to technique number 2, and we can see again the significance value is greater than that 0.025 value. So the only significant differences we can find among techniques are between standard technique and technique number 1. Now we can look up just a little bit here, and we can look at the means of these groups. And so if we look at the mean for standard group, they had a mean global rating of change of 1.67, and the technique number 1 group had a mean change of only 0.566. So those two are statistically significant from each other in their differences. Technique number 2 and standard technique are different numerically, but they are not statistically significant in their differences. So again, in choosing which technique would be most effective, it appears that the standard surgical technique is most effective when it comes to global rating of change, especially compared to technique number 1, but does not appear to be significantly different from technique number 2. When it comes to weeks of return or weeks recovery time in weeks, there are no significant differences among the 3 options. Now, one more thing we can look at to see if this difference between standard technique and technique number 1 is a consistent difference. In other words, we'll see the same sort of result in multiple samples. We can look at the 95% confidence interval. So if we look at the lower bound of standard group and the upper bound of technique number 1, we can see those two boundaries do not overlap. In other words, 0.192 is different than 1.3. If this technique number 1, had an upper bound that was greater than 1.3, then that would indicate the boundaries of these two confidence intervals overlap. And there could be other samples that would have a very different result. In other words, there could be a situation where new technique group number 1 had a global rating of change that could have been 1.3, and the standard group could have had a global rating of change of 1.3, and there'd be no difference between the two groups. So that would indicate that there are other groups out in the population that might have a very different result. What we're seeing in our example here is there is a separation between these two confidence intervals, meaning that in 95% of all the other samples you could collect from this population, there will always be a difference, or there will be a difference between the two groups, standard group versus new technique number 1. So that lends some credibility to the difference, to saying that there will be a consistent difference between these two groups in just about every sample you could collect from the population. So meaning that there's a consistent difference among these two treatments that will typically be there 95% of the time. So that gives some idea of the magnitude of the difference. In other words, it will be very consistent. So in summary, we demonstrated the MANOVA technique, a one-way MANOVA in this case. And so we're able to examine the effect of a treatment on 2 outcome variables. And we also looked at the statistical significance, the effect of the treatments on that. We looked also at the clinical significance relative to effect size, relative to power, and also relative to looking at the confidence intervals. So hopefully you learned something from this technique, and good luck using this technique in your own research.